Tangent lines. All right. So we're talking about a very specific type of line that will intersect with our circles and some very basic, simple geometric relationships that come from them. That's all today's about. Nothing too out of the ordinary. Actually, should be pretty straightforward. So when we, first of all, as we know about circles, there are a variety of things that we talk about. Inside, outside, interior, exterior. There we go. Simple stuff. But there are a variety of lines/segments that do intersect with circles. We've discussed chords. Chords are just any segment that has endpoints on the circle. That's the red one over there. A secant is a line that goes through a circle and doesn't stop. And then the one we're going to specifically elaborate on is that green one over there. That's a tangent line. A tangent line is a line that touches a circle, or really anything, but in our case a circle, at one spot and one spot only. And that spot is called the point of tangency. So we are going to focus specifically on the tangent part of that as we move forward today. Now, being able to identify a tangent is pretty important. So obviously, as we see very bad pickup lines that we might use, we'll talk more along the lines of just can we identify the circle? Now, yes, there's a variety of other things. We know, like small things, how like the diameter is the largest chord in a circle, and there are any number of secants that can happen, though granted there's here one. But the tangent we're talking about is line M over there. That's going to be the big thing we're referring to. So those are the stuff we want to focus on in addition to other things that we know about a circle. So identifying the tangent, which is line M over there, that's what we want. And the point of tangency appears to be at H. So we have a few other things. Find the tangent. What's the tangent? Ah, yes, the tangent is UV. And by the way, we named a tangent. It's a line like any other line with any two points on the line. We just note that the point of tangency is where we're going to be focusing on, which in this case over here, our line is UV. That's our tangent line, excuse me. And again, it's a line, so it is used the line symbol, as you'll note above it. And the point of tangency is at U. Before we get into the math that we're going to focus on, there's also things referred to as common tangents, which can happen fairly frequently. A little bit, well, I don't say super frequently. I guess that'd be not necessarily accurate, but it happens when a tangent is shared. You have, like, for example, we have two tangents over here that are being shared. They're tangent at two different circles. So line L is tangent to both circle A and circle B, as is line M, and this one too. Even though they intersect, they're still common tangents. So they're tangent to two different circles. They can intersect. They can not intersect. Well, these eventually would. But that's what that refers to. So, but what we're going to focus on, the math that we really care about, is our basic theorems, which are fairly straightforward. It's really just this. If you got a tangent to a circle, it's going to be perpendicular to the radius drawn to the point of tangency. Tangent makes a right angle to the center. How about that? Right angle. You see a tangent, it's probably going to make a right angle. And what this does for us, because it makes a right angle, is more often than not, this opens up all of our basic right triangle information. Triangle-specific information, of course. There's triangle sum theorem things that might pop up. But overwhelmingly, the majority of stuff that this brings into is just all of our right triangle information. That means Pythagorean theorem, and it means right triangle trig, basic SOHCAHTOA trig. Those are the two things we're going to focus on. That's it. Our goal, though, is to be able to either make or find those triangles, kind of like we did when we just started studying chords. Remember, we had to identify, like, okay, I'm looking for this chord, so I have to draw a radius from the center to the edge of the chord to make a right triangle. Because at that specific time, remember, we're talking about a perpendicular bisector splits a chord in half. Anyway, same idea. You got to find the right triangle. And we will probably end up making a lot of right triangles, as long as, of course, we identify things as tangent. So, for example, now I'm not always going to be this descriptive, but I have a tangent. That means as soon as I see it's a tangent and it says it's a tangent, that to my brain says, okay, that angle over there, CPQ, that angle is right. Now I put it in here for our first example to make things a little bit easier. But that's not always going to be the case. Eventually we're going to have to infer, all right, it's a tangent, so that means that's a right angle, which means all of my right triangle stuff comes into play. So I'm told PQ, the leg on the bottom, is 5. I'm told CQ, the hypotenuse portion, is 6. I'm asked to find what our CP, one leg of the right triangle, and then the measure of angle C. Okay, so again, tangent, right triangle, right off the bat. Only thing we really need to talk about is our basic, this is a Pythagorean theorem problem. I'm going to be careful because, of course, Pythagorean theorem, a squared plus b squared is c squared. C is always the hypotenuse. It's not difficult. But the most frequently messed up thing here is that we don't recognize that c is the hypotenuse and we do Pythagorean theorem incorrectly. And that's how most of the mistakes get made. They should not be, but that's how most of the mistakes get made. So here, if I know PQ is 5, CQ is 6, and I'm finding CP, I'll say CP is A in essence. So A plus 5 squared is equal to 6 squared. It's just a Pythagorean theorem problem. This is the biggie. You got to pay attention to the fact that my hypotenuse is C. I'll subtract 5 squared from both sides. A is equal to 36 minus 25. A is equal to 11. Sorry, A squared is equal to 11. So A is equal to the square root of 11. And of course only the positive version because we're talking about an actual scenario. Yay! It's just Pythagorean theorem. Sure, I might have to give simplest radical form. I could ask for a decimal approximation. Big deal. Pythagorean theorem. It's just a Pythagorean theorem problem. But then I could also ask for the measure of angle C. That's an acute angle. CPQ. CPQ. I'm asked for this angle. We'll call that theta. I'm told I have 5. I'm told I have 6. SOHCAHTOA trig, everyone, is back. SOHCAHTOA. Okay, that's my angle. With respect to my angle, I know the opposite leg. The opposite leg is 5. The hypotenuse is 6. Opposite hypotenuse, sine. So I'll set up the equation. Sine is opposite over hypotenuse. Sine of theta is opposite over hypotenuse. We'll put it over 1 just to note its proportion. Doesn't really matter because sine of theta is equal to 5 over 6. I got to get rid of sine. I'm taking the sine of theta. I want to get theta by itself. To get rid of sine, I take the inverse sine of both sides. Theta is equal to the inverse sine of 5 over 6. This is obviously going to be rounded. I go to my calculator, I press the second button, 5 divides 6, and I get 56.44-ish. Degrees. That's the extent of the work we have to do. Pythagorean theorem, right triangle trig. That's it. Tangents make right triangles. Don't overcomplicate it. Not sure. I could be like, hey, are those tangents? In both of those diagrams over there are A, B segment, are those segments tangent? Now this, if I'm asked to determine are they, if I'm trying to prove if they are, I just need to know, does the angle that's in between here, does it make a right angle? And if it makes a right angle, that means it has to abide by, that means the triangles has to abide by Pythagorean theorem. So all I'm going to do is I'm just going to check, does Pythagorean theorem work for these ones? And that's actually really very simple. 6, 8, 10. What I will do is I will just put those into Pythagorean theorem. Now obviously there's nothing to solve for, there's no variable, but I'll ask myself, is 6 squared plus 8 squared, is that equal to 10 squared? Whoops, let's move up. There we go. I just asked that question. Does it check out? That's what I'm asking. If the answer is yes, it's a tangent because it makes a right angle. because again, right angles can only be done with right triangles in Pythagorean theorem. There we go. Yes, by the way, 36 plus 64, is that 100? Yes, it is. That's 100 equaling 100. That first one, that's a tangent. BA is a tangent. The second one, oh, this is a good one to note. And keep in mind, this happened a lot with the chords. It's a circle. No matter where in the circle it comes from, if you have something from the center to the edge of the circle, it's a radius. Why that's important is because I note that this is 8.4. That's a radius. So anything else from the center to the edge has to be 8.4. So it might not initially seem like I have this leg, but I do. It's 8.4. It's a radius. Small little things. Oh, that's right. We got to identify what the radius is and utilize it elsewhere. That's all that's here. It's not a lot, but we have to be aware. But with that, now I'm just checking. Does that abide by Pythagorean theorem? I don't know. Is 11.2 squared plus 8.4 squared, does that equal the combined, my whole hypotenuse, is 8.4 plus 5.9. 8.4 plus 5 plus 5.9. Let's go back so we can look at it. Boom. Is that true or not? And if it's true, it abides by Pythagorean theorem. That's a tangent. I'm just going to put some numbers in and double check. I'm going to do 11.2 squared. I'm literally just putting this into my calculator. Plus 8.4 squared. That is not right. Squared. Okay. I'm getting 196. Does that equal, we're going to do, let's see, 8.4 plus 5.9, and I'll square it. That is, ooh, not even close. Nope. They do not equal one another. That is not a tangent. It does not make a right angle because Pythagorean theorem doesn't work. Don't overcomplicate it. There's not much to it. So try these. They're just Pythagorean theorem problems. Pause the video. And let's see what you get. Okay. They're just Pythagorean theorem problems, and we're going to set them up correctly. So the first one, 1.5 squared, because I have leg, that's one leg, other leg, hypotenuse. So 2.5 squared is the last one. So for the first problem, I will have question mark squared plus 1.5 squared equals 2.5 squared. Let's go check out the math. There we go. My question mark needs to be a little bit better. Subtract 1.5 squared. So 2.5 squared minus 1.5 squared. Question mark squared is 4.0, just to be nice. Minus 2.25. 1.75. Hold on, make sure I'm doing this right. Wait, 2.5 squared is 6.25. What am I doing? Aha! Aha! Sorry, 2.5 squared is 6.25. There we go. Minus 2.25. That gives me 4. Square root of 4? Ah! Question mark is 2. Next problem. Did you notice I gave you the radius? The radius is 9, so my hypotenuse is 9 plus 6 is 15. So I have 9 squared plus what will be, well, I'll say 9 plus 6, but we know it's 15 squared. Oh, wait, no, that's not right either. See what I did there? See what I did there? 9 plus 6, that's my hypotenuse. That's C. Man, I could have made that mistake. That would have been really bad. Would have got some bad numbers. Question mark squared, 9 plus 6 squared. 81 plus question mark squared is equal to 15 squared. That's 225. Minus 81. Minus 81 question mark squared is 225. I don't feel like doing that right now. I know it's a perfect square. It's 144. Oh, yeah. 12. Lemon squeezy. That's all they are. Very standard tangent problems. Okay, just so you know, with that out of the way. There are some other ways to do this, like early in flight, Apollo 11 was 120 miles above the Earth. If we know the Earth has a radius of 4,000 miles, you can find out what was the distance from the spacecraft to the Earth's horizon. It's just a Pythagorean theorem problem. This would be 4,000 plus 120. My hypotenuse, 4,000 plus 120. So 4,000 squared plus question mark squared equals 4,120 squared. And the last thing, granted it'll open up a lot of other stuff, is just what happens when two segments are tangent to a circle at the same external point. Surprise! They're the same. Again, today's really straightforward. Tangents are great. Yes, common tangents, not common tangents, excuse me. Two tangents and a common external point, they're the same. So those two expressions are equal to one another. 4 plus 2a equals 5a minus 32. You're going to set them equal to one another, you're going to solve. The only thing you might note is make sure that whatever the variable may be, did I ask you for the variable? Did I ask you to solve for something? This question asks you to solve for a segment, asks you to solve for the measure of the specific tangent. So you'd have to solve for a and then plug back in. So don't get lulled to sleep for that one. Another same problem, they both equal one another. Nothing out of the ordinary, nothing too crazy. Set them equal to one another and solve. But before we go, even though these problems turn out to be really easy, you got to be careful, because what this is eventually going to open up are things like this, where you end up having quadrilaterals. Now, fortunately, they make right triangles. 90 degrees, that's still a thing. We're going to be relating these angles. This outside angle, it's called circumscribed. We'll talk about that later. With this central angle, which in turn also gives us a way to find this arc, because the central angle and the intercepted arc are the same. That's all we got. We'll worry about more of that later. So, let me know if you have any questions. Be good, y'all.